All right. So today we're going to continue our discussion of anomaly with discussing anomaly cancellation, chiral anomaly cancellation, and standard model. If as we go along your way, if there are questions, please ask. We said anomalies are classical symmetries that are not, or classical symmetries or invariances that are not respected by the path integral, meaning that the measure is not respecting it, the path integral measure. In standard model, we have a gauge symmetry, SU2 left. Well, there's a larger group, but SU2 left. It's a chiral symmetry. It's coupled only to left-handed Majoranas. And the gauge transformation of Majorana is like this. Of course, this leaves the action invariant classically. The question is, does it survive quantization? This is a crucial issue because gauge invariant cannot be anomalous. Chiral anomaly must vanish or the theory doesn't make any sense. Is that clear? All right. And the talk word and the word gauging. Do you guys understand what the word gauging means? Just projecting to the invariant sector. That's what people mean by word gauging. All right. Chiral gauge theories. Consider QED coupled to massless fermions in 4 dimensions or any even dimensions. 2, for example, that we'll discuss in a bit. We'll review in a bit. So here's the action. So these are massless fermions, and here's the QED part, the gauge field part. We define gamma 5 this way. In a block diagonal basis, this is just identity minus identity. And when the theory has massless fermions, there are 2 types of gauge transformation. There's a vector transformation, and then there's the axial transformation. The difference is the way they treat the left movers and right movers, right? Left and then right-handed. There are 2 conserved currents associated with it, the vector current and the axial current. The difference is really in gamma 5. By the way, what is the dimension of these? What's the dimension of this current? Operator dimension. What's the dimension of psi? Well, no, it's 3. It's the dimension of, so dimension of psi del psi has dimension d, which means that psi has dimension d minus 1 over 2. This is psi square, psi bar, so it's dimension d minus 1. That's very important. So the thing, these conserved currents corresponding to these gauge symmetries have dimension d minus 1, right? Okay. Del mu j mu nu is 0. So now when you say del mu j mu, if there is anomaly, what is the dimension of that object? It will be d. So it has a del mu j mu, the would-be anomalous term, has dimension energy density. Okay. So classically, this is the conservation laws are these 2, or the word identities are these 2. If you have mass term, they explicitly violate the axial anomaly, but let's not worry about that. That's an explicit violation. But after chiral anomaly, where this term is classically at the level of the action 0, but it acquires a non-vanishing value because of the quantum corrections. As an example of this, we discussed QED in 1 plus 1 dimensions, massless QED in 1 plus 1 dimensions. Now the term massless needs to be put in code. Do you remember why? Yeah. Well, yeah, that's right. Okay, that's right. So we split psi into psi plus psi minus, right? Now the Lagrangian splits in the following way, right? So psi plus, psi minus, psi minus. These are left and right movers that they decouple, right? If I set if I set a mu equals 0, the covariant derivative becomes the regular derivative. So it's pre-explicit that these are left and right movers. The conserved currents are has to do with the fact that the number of the left movers and right movers are independently conserved, right? So when we say that, yeah, okay, so I think this is clear. Any questions? Actually, I'm not sure. I'm not sure. No, this is massless. It's honest to goodness massless because so the fermion is yeah, no, the propagator for the fermion. Yeah, I think my comment was wrong. My comment was wrong. Yeah, I think we still call that massless, and it's perfectly fine. For a second, I got confused regarding the fermion propagator. Although I don't remember the formula in showing your theory. So, yeah. Is it clear what I'm saying? So at the level of the action, of course, photon is massless and fermion is massless. We saw that photon gets a mass quantum mechanically because of the corrections. So I don't remember what happened in the Schrödinger model. I think fermion remains massless. There are no quantum corrections to that. I don't remember. I think that's a true statement. But anyway, at this level, we were just talking about the classical action. All right, so in QED2, photon is massive. We have two transformations. The vector that treats right movers and left movers the same, and the axial one that treats them with a relative minus sign in the gauge transformations. We would like to see if there are any anomalies. We use a trick. The trick we use is we use this vacuum polarization, right? So the anomaly has to do with this object. The anomaly has to do with this object, right? This is J mu. This is an external source, A mu, which is A mu. Yeah. This is an external source, and this is the one loop correction to it. So to calculate that, we start with this amputated diagram that we calculate in vacuum polarization. This was the answer for it. When m of psi is 0, this x times 1 minus x and this minus x, 1 minus x, they cancel. So you could do this integral explicitly. As a matter of fact, 1 over q squared comes out, and this is just 1. And you get that when m psi squared is 0, we actually have the correction, the one loop correction explicitly this way. Then we said that, so this implies that there's a photon mass, and this is consistent with Ward identities because we have a massless fermion running in the loops. If you remember, the argument that was saying that Ward identities requires masslessness of the photon was assuming that there are no poles in there were no massless modes running in the loops. That was the caveat to it. Yeah.
Aren't we calculating the one connection?
The one loop, yeah. Good. So let me just correct that. Anomaly is always quantum. So we're not calculating an anomaly correction. We're calculating the anomaly at one loop. Because anomaly, of course, is 0 at 0 loops, right? By definition. Anomaly is about starts at one loop. So we're just calculating the anomaly at one loop. All right. So the way we calculated axial anomaly from vacuum polarization by looking at this diagram was noticing that we could just take this 1-point function, replace it with a nu, and this is just the vacuum polarization expression we just used. We just calculated, we plug it in, this is the answer. If this is quick, there's a more detailed discussion of this in testing. Schroeder. Now you could explicitly check that this was the case for the vector current. You could explicitly check that after Fourier transform Q mu, well, this is obvious. Q mu times this is 0. Right? Q mu contracted with this is 0. It's just it being transverse, right? So vector transformation is not anomalous. So we'll have to calculate the axial one. Now the axial one in d equal 2 is easily could be calculated using a recycling of the same calculation, using the fact that gamma 5, gamma mu is epsilon mu nu gamma nu. How is this helping? Well, the difference between JV and J mu was really gamma 5 in the middle. So you could package this in this form. So just you recycle the same calculation, you find this epsilon mu nu is outside. Now when you do the contractions, it no longer vanishes, and you find that using Feynman diagrams, in particular this Feynman diagram, this one loop Feynman diagram, well, we use this guy, right? Calculated an anomaly, and we found that it's proportional to F mu nu, right? So now I want you guys to remember del mu J had dimension of D. The right-hand side has to have dimension of D. E F mu nu in this notation has dimension D. Right? Just keep track of dimensions. Now, if you were in, well, okay, maybe I'll comment on this later. For example, if you're in higher dimensions, if you were in, so this is in 2 dimensions, right? So we're doing this calculation d equal 2, and we found that del mu J mu is like EF mu nu in terms of dimension counting. If we were in 4 dimensions, could an equation of this type hold? Just by dimension counting, you wouldn't be able to make it work. I'll comment on this. And then already based on dimension counting, you have an expectation for what this should be. You could just naively guess it's going to be like E F mu nu squared, something like that. Maybe it's more complicated. It's indeed more complicated. That epsilon mu nu is replaced by epsilon mu nu rho lambda. We're going to calculate that. All right. This is axial anomaly in d equal 2, which means that there exists no regulator that can preserve both axial and vector currents. Axial current is not conserved, charge is not conserved, but this is disastrous, right? The gauge theory doesn't make sense. We went over this in a different way using the so-called Fujikawa method. So this was Feynman diagram at one loop. Now we're going to do path integral method, right? In the path integral method, well, this is sort of obvious. This is just saying the invariance of the action under this transformation. In the path integral form, we know that the action is invariant under the axial gauge transformation. The question that remains is the measure invariant? Well, if you want to think about the measure, you could take your fermionic fields and expand them in terms of the solution of the Dirac equation. You look at orthonormal eigenfunctions of the Dirac operator, you expand it in terms of those. These AMs and A prime M's are anti-commuting, they're Grassmannian. So with that, this d psi bar becomes just pi over m multiplication of integrals over these Grassmann variables. Good. Now the anomaly comes from the fact that under axial gauge transformation, this guy picks up a Jacobian, J minus 2. So how do we calculate that? It's easy. Well, you remember that so my psi x was just expanded in terms of solutions of Dirac equation. I made them orthonormal, so I can think of AM in the form of this integral, space integral. Now, under the axial transformation, this is how psi x transforms. That immediately tells you that AM transforms this way. Now I'm going to call this CMN, and basically what you obtain is that AM. What you obtain is this. You find that AM goes to AM plus sum over N CMN AN. Right? And CMN is just basically this integral. Of course, it's gauge dependent. But we're going to be interested in the determinant on it. Now, this sum is infinite. We got to regulate this. This blows up, not surprisingly. All right, so here's the expression. The canonical way to regulate this, because these are eigenfunctions of the Dirac operator, is just to regulate them by something that exponentially suppresses the larger the eigenfunctions that correspond to larger eigenvalues, right? So that's just ID slash squared over M squared inside this expression, and taking the limit of M going to infinity, right? Is that good? So we have to calculate this trace, basically. That's all we need to calculate. Now, I said that we have this nice identity, which is basically, you can expand ID slash squared in terms of the D squared, right? The covariant difference squared, plus E over 2F mu nu. Sigma mu nu is just a representation of J mu nu. Remember what it was? Anyone? Correct. Yeah, I over 2 commutator gamma mu over. I think it was I over 2 or something. Yeah, gamma mu gamma. All right. So now the task was to expand this in large M. I'm going to do it now, and you'll see. I'm going to come back to it, repeat the same calculation in D equal 4. Up to here is identical. Up to here, I don't assume anything about the dimension. Here's the very first place I use the dimensionality. We saw that in D equal 2, gamma 5, the trace of it is 0, and I have this identity. So we expanded it, and we found that log of J is minus E over M. This expression, the Jacobian. Oh, sorry, this was a comment that was relevant for the previous lecture. You know that now. Hopefully you don't get confused. So we found the Jacobian, and then as a result, we found the operator quotient this way. But from this line onwards, we use these identities in the expansion of this. So when you expand this, oh, sorry, my bad. Sorry, my bad. I think over here, from this line and this up to, whoops. Well, okay, you'll see. I'll repeat this calculation. I'll repeat this calculation in D equal 4. You'll see. All right. So axial anomaly in D equal 4. All of this is the same. Determinant of 1 over, yeah. Electron gaining a mass at 1 loop correction. So it's tricky to interpret it that way because no, because I don't think that's correct. Maybe there's something about 2 dimensions that's special. But for one thing, the mass term, so del mu of J mu, right, became epsilon mu nu schematically, right? E F mu nu. Now a master would be something like this, right? It's not a priori clear to me how to interpret a term like this way. As a matter of fact, I don't think it does. It would transform, it would translate this way. Nicely. We will see in 4 dimensions, it's very explicit. In 4 dimensions, this term, actually 2 as well, I think, is topological. The anomaly term. The anomaly term is topological. Whereas this clearly is a local, there's local physics associated with it. I'll comment on that. So no, I don't think that it could be interpreted as massive. So determinant of the 1 plus c is what we want to calculate. That's the Jacobian. Of course, we're going to, as usual, exponentiate this. Well, take the exponential of trace of log of 1 plus c and view this as a correction to the action, right? Or otherwise, what's this on the right-hand side of the conservation law? We're interested in one loop, so we're going to truncate as x with trace of c, right? So here's trace of c. It's an integral over alpha of x. This guy. We have to regulate the trace. This is where we are, right? Up to here, we're good. This up to here, the calculation was the same in d equal 2, d equal 4, all of that. Next step, we're gonna expand this. No, sorry. No, what I said is incorrect. Sorry, what I said is incorrect.
Sigma not epsilon.
Sorry?
Like how we get the
Yeah, no, this is incorrect. Let me go slower. What I should copy here is this. Is this equation. Yeah, oops. What I should copy is this thing. Copy. Paste. Right? So trace of that. So this, I'm just writing this bit. After I'm taking this bit and regulating it, right? So let me. This is the regulator. There should be what?
ID slash square.
Oh, there's a 2 missing. Yes. And then the next step to remember is that d slash 2 was d squared plus, so it was minus d squared plus e over 2 f mu nu sigma mu nu. So now this is fully general. The next, yeah, this was the step that I was talking about. Next step is to expand in this expression in large M. I'm gonna get gamma 5 is gamma 5. I'm gonna expand this guy in large M. Here's the 0th order term. Here's the 1st order term, 1 over m squared, this guy. This is id slash squared. There is 1 over 2m4 id slash 2 power 4 plus dot dot dot. All right. So let's zoom here. Are you guys with me here? Sorry, I think so up to here everything is 3 dimensions. We're good. Gamma 5 and 2, 4, 6, whatever dimensions, even dimension looks like this. So the trace of it is 0. This term drops out. Good. Right? As it should. So we have to focus on this term. Let's look at this term. Actually, so what are the remaining terms? The remaining term, oh, actually, let's look at this. This term is d squared gamma 5. That term drops out too. Right? So I have this term that remains. Because these have epsilon mu nu indices. This term drops out as well. If I expand it, there will be an f mu nu term. And yeah, the term that comes from the expansion of all of these expressions with the d squared removed, they resum to this term. Wait, is that? Yeah, no, that's correct. That's correct. Because the first order correction of this term is this. The second order correction of it comes from this term, and so on and so forth. Right? What I've done is that I've taken this expression and expanded it to the first order in F. Any expression that has no, so expand this, any expression that has no F's in it will vanish. Right? Because there's had gamma 5, trace of that is 0. So the first order in F, this is the expression, there's F squared. So let's focus on this. In D equal 2, trace of gamma 5 sigma mu nu, that I have to calculate here is I epsilon mu nu. So this term gave the anomaly. This was the anomaly term. In D equal 4, trace of gamma 5 sigma mu nu is 0. This term vanishes. We got to go to the next order, which is F squared. But that's good news. F squared comes next to it with E squared. That's the right dimensionality, right? Where's the origin of this dimensionality mismatch is factors of M. All right. So in D equal 4, we have trace of gamma 5, sigma mu nu, sigma rho alpha, lambda rho, because the second order term will involve these expressions. They're minus 4 epsilon mu nu lambda rho. They resum to this thing. Voila, that's your anomaly. This is your anomaly term. You get minus E squared over 16 pi squared, epsilon mu nu rho lambda, F mu nu lambda rho. One important thing, any expression of this form, whatever appears on the right-hand side in arbitrary dimension, right, better be gauge invariance. Gauge invariant, right? This is a gauge invariant combination. It's second order in F, but it's not the Yang-Mills kinetic term. What is this term? This is the topological term. This is the theta term that we were adding, right? It was CP violating term. So recall that in writing the action for gauge fields, we wrote, maybe we wrote F a little bit closer to the indices. Minus 4 F mu nu, F mu nu. There was this theta, which was the theta of the size of this term, the coupling for the size of this term. I said that this is conventional. Remember, I wrote to get E squared, I call it G squared, or 64 pi squared. Now you see why, because of this expression, right? Epsilon mu nu or lambda, this guy. This is the CP violating gauge invariant term. This term is topological. It does not depend on the metric. For those of you guys who know differential geometry, this is just F wedge F. So this is the differential geometry way of writing it. It's independent of the metric, therefore obviously topological. What's the kinetic term written in terms of differential forms? Anyone?
Yeah.
No.
All right. Please stop.
So in 4 dimensions, right? This is the formula. No, this is it. Remember that star has G mu nu in it. The only appearance of G mu nu is the Hodge dual. Well, okay, this is not a course on topology or geometry. Good? Are we good? Any questions?
Looking at this term, so again, it is topological, but that thing is like the whole expression that's lambda rho times the that should be done cancel. That thing is essentially E dot B.
Is what?
E dot B.
Oh, in the yes, it's E dot B.
Which is like it's a local. I don't understand in which sense. Like, so there you said that the first line is topological, but M is defined with. Well, I guess I'm confused.
So okay, let me clarify this. When I say it's topological, so topological means what here? All right. There are various notions of local, right? the notion of local that is like somewhat more abstract and is more commonly used in high energy physics, which is, I think it encompasses all the other notions in a nice way, is we say a theory is local if you define it in flat space. I know how to define it in arbitrary curve background. Right? Why is that? Because locally, every arbitrary curved smooth background looks like flat space. So I can just, like think of the operator algebra here, here, right? Here, what we mean by local, it means that its response to the metric is zero. It doesn't change with the metric. So the form of it is E dot B in flat space, indeed. But if you introduce some sort of background metric, some curvature, it won't change. Well, the form of the expression E dot B is kind of like flat, designed for flat space. I will come back to this in the instanton discussion. Yeah.
So what you're trying to say is that this E dot B term doesn't depend on the background which I'm choosing.
Yeah. Well, I'll comment on this in the instanton section. I think this was like a detour. I just wanted to say it, but I'll comment on. We'll come back to this and extend the field configuration. That's going to be all about this stuff. All right. So again, quick dimension counting. ID slash squared is minus D squared plus E over 2 sigma mu nu F mu nu. This immediately tells you that F mu nu E has dimension 2. We know that J mu has dimension D minus 1. So if J is sidebar, yeah, so that's it. D mu J mu is dimension D. So this is dimension D, and this guy is dimension 2 in arbitrary space-time dimensions. So if the object is to be created out of EF mu nu, in D equal 2 is normal, is natural, there's EF, and D4 is E squared F squared, and D6 E cube F cube. Good. So now, next slide is about axial and all different Feynman diagrams, but before, I think what I did with that. Before that, let me make you guys guess. So in the case of D equal 2, we use this diagram, well, or the amputated version to calculate the this, right? What is the Feynman what is the Feynman diagram that I have to draw if in 4 dimensions that would be analogous to this, if you have a guess? So remember how this calculation worked, right? So this guy introduced some A mu, right? There was some pi mu nu here, right? This was some eta mu nu minus q mu over q squared or something, right? There was E squared E over pi, blah, blah, blah. And there was A mu here. And this gave us J mu nu. When we took a derivative out of that, we constructed that derivative in this gave us an F. Now we know that in 4 dimensions, it's going to look like F squared and 2 of these guys. So do you have a guess at what it's supposed to, what's going to be look like? What diagram is going to help us? First of all, if I calculate this diagram, well, okay, no, let me not over-explain. Because the vacuum polarization, if you remember, the calculation was just true in all dimensions. It's true that in D equal 4, that there's no mass for the photon. Well, actually, no, I shouldn't even say that. That the expressions are not you can't integrate them nicely and we won't refine them. Right? Do you have a guess? There's gonna be two of these factors, right? Because we need to build two F's, right? This F came from a mu and some derivative thingy. So in D equal 2, we use this diagram, and in D equal 4, the diagram that gives us the anomaly is this guy. And the thing that, so the anomaly is this guy, and the analogous thing for vacuum polarization is going to be this diagram. Sometimes this is called the triangle diagram. Is it clear why? Because people draw this way and I didn't. Right? This is the triangle diagram. It's still fermion running in the loop, but there are three external legs. There's a way of calculating this in Feynman diagrams. There's a way of calculating the axial anomaly in Feynman diagrams. Using this diagram is called Adler-Bell-Jaquiev, and there is a detailed derivation of this in Peskin-Schroeder. But we saw a quicker version of how to get the answer from path integrals, right? All right. Any question?
Where is that cross the source area section coming from?
It's coming look, here. Ooh. Yep, here. So it's background field methods. You look at this expression, and basically this calculation boils down to insertion of a background field, right? That this is the background field. This is you're looking at this one loop. This is like a 1-point function in the presence of this background, in the presence of this source, right? So the 1-point function of the source is interpreted as some background field, and you're doing your calculations in the presence of that background. For example, you're calculating this diagram, right? In the presence of that background, which means that the answer at the first order is going to look like this. Now, in 4 dimensions, at the first order, there is this term, but it vanishes, right? So you have to go to a higher order, right? So this is the higher order in the presence of the source, right? And higher order, and higher order. These are all they're there in arbitrary dimensions, but the dominant one is the first one, right? It vanishes in equal 4. It's non-vanishing in equal 2. Yeah. I know that discussion was a little bit rushed, so I think you guys will benefit from reading Peskin-Schroeder that part. I was a little bit disorganized in that presentation. A year from now, I'll do a better job. All right. Any other questions? So, what are we trying to do? We're doing this calculation of chiral anomaly, right? And the goal was that we built this beautiful model called standard model of particle physics. It has chiral gauge, we had chiral gauge invariance, right? We had massless fermions. Remember that fermions were massless before spontaneous symmetry breaking. Massless fermions that were left-handed Majoranas and were coupled with some chiral gauge theory, right? We coupled only the left-handed sector. We want to know if that's a sensible thing to do. Now, the amazing thing, it blows my mind to even think about it, is that when we presented standard model of particle physics, the number of particle generation, charges, those representation, I just gave you guys as, this is it, as facts. those numbers, the crucial details of those numbers are essential for getting chiral anomaly. It's not the unique way of getting it, but you will see, well, we're going to go through the calculation. You will see that, oh, if you mess up with some of these numbers, like representations, like charges of quarks, they could, if like you mess them up, some of the anomalies will not cancel. Your theory, you just have to throw out the theory. It doesn't make any sense. So as a warm-up, let's do the calculation of massless QED in 4 dimensions to see if this theory makes sense. We want to see if, well, sorry. We want to see if there is a sense in which you could make sense of chiral gauge transformation, axial gauge transformations in QED4. So here's one important thing I have to tell you that you might find confusing. This is just experience from like working with Majoranas and Weil, and you're gonna go through these and you're gonna see massless QED, your electron is left-handed and right-handed. If you want to get this calculation simpler, what you want to do is you want to think of this as 2 left-handed modes. One of them is E left. The other one is ER bar. So you have 2 left-handed modes, in a sense. Yeah, this is part of that story of splitting everything in terms of Majoranas, right? Now I want to calculate the vector and axial anomalies. So here's how these E and E bar transform under vector and axial. Under vector, this has charge 1 and -1. The vector was treating the left-handed and right-handed the same way, but then I took the conjugate to bring it up, so that's why I split. Axial was treating left and right the same, but opposite, but I took the conjugate, so it's like this. All right, so now we're in 4 dimensions. This is the diagram we're calculating, right? And basically, all that matters is that your answers are gonna get a charge factor from each of these insertions. So let's say this is axial, axial, axial. Is that clear what I'm saying? So TAAA, what runs in the loop? There's E that runs in the loop and E bar that runs in the loop. You have to sum both of them. E that runs in the loop will contribute as QA cube. E bar that runs in the loop will contribute as QA cube of E bar. So here it is, 1 + 1, 2. Axial anomaly. The theory is nonsense. So if I have vector here, and vector here, right? QV cube of E, QV cube of E bar, that cancels out. No anomaly for the vector part. But now in 3 dimensions, I can have vector, axial, axial, vector, vector, axial. Here are where they are. Vector, vector, axial is anomalous. Does it make sense? Guys, these quick tricks take some getting used to what I'm calculating, but I'll actually try to comment on this a little bit more.
So you third term expansion.
Sorry, say it again.
So we're computing the third order term expansion.
Second order. So there's, in terms of orders of F, 0th order cancels, 1st order cancels, F squared. We're calculating F squared term. Yeah. So you could view this as the response of the background to the introduction to this guy. Well, okay, I leave it to you guys to work out these calculations. But
There's like the A, which is something that transits with.
so let's see, how can I explain this a little bit better? what this represents is the following. Well, okay, sorry. I'll come, I think I'll come back to this, okay? If it's not clear. Yeah, I'll come back to this. Actually, right here. Right here. The expression. How do I want to say this? Yeah, the expression looks like this. If we calculate, so we calculate chiral anomaly, this expression, and where is it? This expression, and for abelian gauge theory, if we calculate this for non-abelian gauge theory, there will be a factor sitting outside, and that factor is trace of TA, TB, TC. This is trace, this is the anti-commutator. Now, the point is that our representation is now reducible. So these TA, TB, TCs are diagonal matrices with QAs and QVs. Right? So there is A in here. A refers to the fact that I'm putting the same charge on both, as opposed to, sorry, which one? Same charge or the opposite? One of them. There are two configurations, right? It's a representation theory statement. Good. This is the general form to remember. Every time, so look at this there. We're doing the calculation using the triangle diagram, right? Every interaction will have an insertion of one of these guys. Right? Now, when you have an abelian setup, right? Your representations are, your ERFs are one-dimensional, but your representations are reducible, right? So this is like Q1, Q2. Right? And then the axial and versus vector have to do with these choices. So when I put A here, it's about which choice of matrix is it? Is it 1 minus 1, 1 minus 1, or 1, 1? Right? But the way that I keep track of it is every interaction comes with a representation for the interaction. This is a fermion representation. Now I happen to package side plot, side left and side right together. The representation is reducible for the abelian case, right? So these guys are some diagonal matrices. So there are various choices I can have. So, all right, is this clear? Now, the expression to keep in mind is precisely this. Standard model of particle physics is four-dimensional. It's a four-dimensional theory. We have a gauge group, SU3 times SU2 left times U1 hypercharge. We have massless photons, massless fermions, which are quarks and leptons. You remember the representation theory. I have to calculate this diagram and calculate the anomaly for all possible choices. So what are the TAs here for the case of standard model? So TAs of the standard model are coming from, there is the SU3, so that will be, we can call it T alpha. The Gelman matrices are corresponding to SU3. There will be TAs of SU2 left, right? And then there will be QY, Y of U1 hypercharge. Now, I'm looking at this diagram. I'm gonna have all sorts of different combinations, right? I can put a gluon here, or sorry, I can have a gluon interaction here. vice versa. Of course, if I put a gluon here, what's running in the loop? There are all sorts of things that run in the loop. There are leptons that run in the loop, right? And then there are quarks that run in the loop. If you put a quark here, so if you put a T alpha here, leptons are not gonna run in the loop. That term is not getting anything from the leptons, right? We have to check all of these terms. So previously, in the case of electron, I was writing T, A, V, all of those combinations, right? So now I'm gonna say the following. If I put this, so I'm gonna use this notation. T, if it's a gluon, right? I'm gonna put 3. If it's for example, SU2, I'm gonna put 2. If it's this guy, I'm gonna put 1. I have to calculate this anomaly coefficient for 333, 311, 312, all of that. Now, first thing that you notice is that this coefficient is proportional to ETA, this guy. This tells you that the anomaly is invariant under relabeling of ABC, permutations of ABC. So I only need to, I don't care about the order, but I have to calculate all of them. And interestingly, if you put the right numbers of charges, because the charges come in, all of them cancel the Anomaly particle physics. We're going to go through that. Is the principle clear? Right? I'm going to do 2 sample calculations, but the rest is in your homework. All right. So first, before the build-up to a standard model is a simpler calculation. Let's say you have SU2, right? So you're only SU2. You only have you have massive fermions coupled to SU2, and your TAs are just the Pauli matrices. Oh God, I can't talk. That means that this anti-commutator is 2 delta BC, and our coefficient is like this. But this vanishes, right? That instantly tells you that A222 is 0. That's a very quick calculation. Can anyone, you guys guess what happens? Can you guess what happens if you put 333? So you'll have to replace this with Gelman matrices. You're going to get something faster. I'm going to repeat. I'm going to do the calculation, but of course the answer will vary. Now, next, let's calculate fermions charged under U1 times SU2. So A222 will vanish. I still have to calculate A122, 112, 111. So a claim 112 vanishes. Why? Just look at this structure. I claim that the 112 vanishes. Why is that? You get the trace of Pauli's. Pauli's are traceless. Yes. By the same logic, 113 is also 0. Gilman matrices are traceless. Any SUN, generators of SUN are traceless. So voila, that's one piece of the story. But the part that I have to calculate is 111 and 122. Right? 111, we already did the calculation. Let's not worry about that. Let's calculate 122. So 122 is Q of TBTC. These are Pauli matrices. There's delta BC. This is what comes out. This is the answer to your question. It's not, it's true that the Q is one dimensional, but this is trace of Q. Right? It's a reducible representation. All right. So here it is. Consider the SU2 doublet, for example, leptons, so that we don't need to worry about anything, the quarks. P left lepton, the left-handed lepton, which was the left-handed neutrino, left-handed part of the electron, are in this doublet. This is the representation. What's the anomaly? Can you make sense of this expression I've written down? So half is this half, right? What is this minus half time two?
Minus half is how much charge and because there are two.
Right, there's up there. This is an SU2 doublet. Both of them have minus half charge, so they add up, and you get there's a half in front, so you get minus half. This is anomalous. Bad. The anomaly doesn't vanish. What if you had a quark? You had quark SU2 doublets. So PLQ is 326, right? The calculation is the same. Now the charge is 6. Right? There are two of them, SU2 doublet, 3 for 3 colors. Still not vanishing. Bad. But here's the catch. The total anomaly vanishes if you add them up. Right? Because when I draw this diagram, Q is U1. These are SU2 stuff. I should add up the leptons and quarks, and the charge 1/6, if you mess with it, will not cancel. The theory won't make sense. We just calculate an anomaly, Carl anomaly in standard model. It has to vanish. Otherwise, when people calculate this, so you have to appreciate that when the first one this was discovered, it was quite surprising. Yeah.
So historically, the standard model come first and then they put the anomaly or they design the standard model to be anomaly.
No, I don't know actually. It's true. I wasn't around back then, but I think anomaly calculations were later. I think anomaly people started understand. Like I don't know the history of it really, but people started understanding anomaly really well. Like in late 70s, early 80s. Whereas standard model, the need for 3 generation like quarks and all of that is like people were trying to make sense of a theory of strong force, right? Because there were suggestions, like there was a lot of that for a very long time. People doubted that QCD exists, right? Actually, so depends, standard model particle physics depends when you say it was standard model. Is the Higgs mechanism, I guess, you have to look at the timing of anomaly versus Higgs. Yeah.
This one question was, why are we looking at the anomaly, like all the particles? I should be concerned about just the current anomaly, the electron current.
No, you're calculating that you're calculating J mu. That is a SU2 current at one loop. You don't decide what runs in the loop, right? Well, these are quantum corrections, right? You don't decide the loops. The loops know about the particle content. Yeah, that's importantly quantum. So in standard model, the gauge group is SU3 left, SU2, SU3 color, SU2 left times U1 hypercharge. Let's do. I have all of these, right? I have A333, A133, 332, 111, 222. 222 we said is 0. A333 is also 0 because of the relations for Gell-Mann matrices. Now let's calculate A333. No, A33. Too many threes. So it corresponds to this. I'm sorry, this is bad. My bad. I already changed notation. I think I had said that I'm going to use alpha, beta here, alpha, beta, gamma, gamma. Right? All right. So this is this anti-commutator for Gell-Mann matrices. Of course, the T gamma term vanishes. Why? Because Gell-Mann matrices are traceless. All right, so that term goes away. You're left with this. There's this factor of 4. Let's not worry about it. But basically, to calculate 133, we have to sum over all quarks, not leptons. Why quarks? Because those are the only things that couple to gluons, right? They're hypercharges. All right. There's a 3 sitting outside. This is the number of generations. It won't change the anomaly. So you see, okay. Then, what are the quarks? There is left-handed Q quarks different generations, right? Transform in this representation. There are two of them, up and down. So 6. There's 2 times 6. Then you have remember we had the right-handed stuff, but I said that the good thing to do is to look at the corresponding Maranas on the other side that they're transformed in this representation. This is the left-handed part of the right-handed Marana. Got it? That's why we're insisting on Maranas. Because you can get yourself into like a lot of trouble. So this transforms in 3 bar because I conjugated, right? 1 minus 2/3, the charge has flipped sign. 3 bar, 1 1/3. I only have one of this, right? Because it's an SU2 singlet. I have only one of this, minus 2/3, a third, they add up to 0. All right, and your homework here will prove that all the other ones are 0. The really tricky one, well, the really cool one, I'll do this next week as well. It's 1 1 1. It's the one that you add more terms, they don't cancel. All right, so in summary, we see that anomalies of standard model cancel, and this took non-trivial relations between the number of species, quantum numbers of quarks, and leptons. So standard model is, even though we couldn't argue where these representation numbers came from, they have some nice properties that are required by the quantum consistency of the theory.
So number of generations, it's still not.
I don't remember what happened in 1 1 1. I didn't use it up to now. I don't remember what happened in 1 1. I think number of generations. Yeah, no, I think no. Depends a lot. The number of generations will be related to what matter content you introduce. Yeah. Okay, it's subtle. It's subtle. Yeah, it will depend because okay, standard you might make a case for a standard model, but you might say how standard model could have been different, right? Introducing various sectors, then things can go bad pretty poorly. I think the number of species is used some of the cancellations. You'll do it in your homework, but I'll also confirm with you guys next week. All right, summary. What did we do today? We discussed Carl anomaly of massless fermions, right? Which was just whether massless fermions will have both the axial and vector gauge transformations. As it says in a sensible theory, this should work. So is massless QED in 4 dimensions a sensible theory or not? It's not, because it has an anomaly, right? We calculated, we saw that AAA was 0, T of AAA. It was 2, sorry. In D equal 2, we saw that the anomaly was coming from just this guy, vacuum polarization. And we saw that it was just proportional to EF mu, proper things contracted. The dimensionality of this was 2 in arbitrary dimensions. How did they argue for this? Just look at the expansion of this. Oops, minus D squared plus E squared F mu da da da. So they have the same dimension. The dimensionality is 2, right? Now the dimensionality of J was D minus 1, del mu J minus 1, J mu is going to be dimension D. In D equal 2, we had this nice relation that was telling us that EF mu nu, epsilon mu nu is basically the anomaly. In 4 dimensions, the diagram was a little more complicated. There was this, here, I already put the generators in there, because having in mind various representations, right? And this has 2 factors of E F mu nu, right? And that's required by dimension counting because 2 times 2 is 4. All right. This was Yeah, okay, what else did we say, actually? Yeah, we started doing these calculations in Sano model, and we saw that, well, at least for the few that I calculated, they vanish, right? So it's good. But this crucially dependent on the matter content representations. Again, as you're seeing this, we saw this in the past, the one loop calculations are often fixed by representation, matter content, right? So this is something really interesting. Like a one loop calculation, something, this is exactly your question. Something that looks innocent at one loop starts exploring, sees pretty much everything that's coupled to it. Right? So it knows secretly about a lot of all sorts of matter content. But again, a lot of the times, as we saw in calculation, the beta function has one loop, or in this case, a lot of times these are fixed by representation theory, particle content, right? All right, any last questions? Okay.